Hello, everybody. My name is Marilena Müller, and I am currently a PhD student in Heidelberg, Germany. First of all, thank you so much to the organizers that I'm given the opportunity to share some of my work with you at the Stochastiktage. What I will present today is a testing problem concerning Hawkes processes, which is joint work with my supervisor, Enno Mammen. We are looking at a counting process on the positive real line. Such a counting process is called Hawkes process if the conditional intensity function has the following form. We have a so-called immigration rate mu, which is positive, plus a second term, which is depending on the history of the counting process. So when we look at lambda in the instance t, lambda is growing with a factor given by mu at the point t minus s, which is the time-wise distance of s to t for each jump point s of n. Often mu would be found to be decreasing, as an event further in the past might have less of an impact on the intensity than time-wise closer events. Also, the assumption of bounded support is not far-fetched, as events might lose its influence completely after some time has passed. There are some typical applications, earthquake occurrences, meaning that an earthquake triggers additional aftershocks. The same holds for populations. For example, insects might immigrate to another population and then give birth to additional insects. Another big application is finance. If agents buy stocks, other agents do the same. The original model is particularly great as we have stationarity. There's a problem though, as you would actually want nu and mu to be time variant in t, which would mean that one could model, for example, the insect population such that the immigration rate is not the same in each season, which is sensible. The same holds for the stock market example, as apparently the markets are most active right after opening and close to closing time. For our approach, we now introduce local stationary Hawkes processes. We have the time varying nu and mu, and we look at the time in an asymptotic framework. Instead of looking at the whole observed process from 0 to big T, we're looking at a grid from 0 to 1. And as T gets bigger, the grid gets finer, instead of the interval getting bigger. We then get the opportunity to localize around a fixed point T0 over T. If we then make assumptions on nu and mu, we obtain grid properties. Not surprisingly, we assume existence of partial derivatives as well as a non-explosion property, meaning that the integral over mu has spectral radius smaller than 1 in the multidimensional case. We are going to denote the true functions with an odd. So now I will introduce the testing problem. We are observing two Hawkes processes, N1 and N2, and we want to see whether they coincide at a fixed point T0 over T, in the sense that the underlying nu and mu coincide at that point, which obviously doesn't mean that the events align in a way. Cleverly, we choose the quantities big delta and tau hat and define a characteristic quantity theta hat for each of the two processes, and then look at the distance as the test statistic. So why do we look at that theta? I will give you the intuition of that. Theta is minimizing such a contrast as here in the remark below. We use a local smoothing technique, meaning that we have a bandwidth h and a kernel L and minimize over the distance between the two lambda and this skeleton of the intensity function. Here the theta naught represents the immigration rate mu at T naught over T, and the sum of the remaining coefficients of theta together with the B-spline basis phi j, then mimic the true reproduction mu. This is basically a least squares idea as we minimize over the square of the error. Theta hat is then given by the inverse of delta, as it is written above, times the tau hat. The work now consists of handling those terms, delta, tau. What we are using are two very important properties. First of all, we can use a Dudmeyer decomposition. The n is hard to manage, so we split it into the intensity function, still hard to manage, and a martingale, which is manageable. Now, the second important tool, we can write lambda and its expectation in terms of a martingale, and depending elsewise only on the true nu and the true mu. So we divide tau into a tau A and a tau B, and find, as you see in the lemma below, that the tau B's are fairly close to each other. That's the first step. What then remains to be considered is the difference of the tau hat A's and the inverse of the delta. We remember that tau has this form as given by the kernel smoothing. We already know that the difficulty lies in the two integrators ns and nu. And the result here is the asymptotic distribution of tau hat A. So how does one get such a limit theorem in such a highly dependent setting? We use a fairly known property of Hawkes processes, and namely its cluster representation. Each ancestor that immigrated to the population triggers a family tree of descendants, which then form a cluster. The clusters are obviously not observable, but as we assumed our non-explosion criterion, we have a finite cluster. Intuitively, in the sense that if the mean birth rate is below 1 in our non-explosion criterion per event, we can expect finiteness. So we are looking at the whole counting process n, given in green here, and we want to split the observed timeline alternatingly into those red longer intervals and blue shorter intervals. The processes M now include all clusters corresponding to ancestors which immigrated in the red interval. This means that M spills over into the blue interval afterwards. If we thus choose the smaller intervals big enough, the processes M are IID, as we somehow assumed with locus stationarity that mu and nu do not change too much in the interval in which we observed n. The length of the blue intervals is depending on the cluster length, which has exponential tails, which is convenient and was shown a while ago. So in a nutshell, we choose the blue intervals as big as they have to be, and then choose the red ones large enough. Then the sum of the processes M is in distribution close to n. We can then use a central limit theorem and obtain an asymptotic distribution of the tau hat A. The corresponding variance is to be calculated with our tools, and an additional result about the fourth moment of n. One then only has to calculate the expectation of delta, which is then easy, and we see that our test statistic T asymptotically has a chi-square distribution. What there should be done in the future are simulation studies or data studies. Problems here are that one needs a lot of events in the local interval around our fixed point T0 over T. which makes it hard to be applicable for any arbitrary problem. In finance, there are in these situations like limit order book examples, where you have more than enough events to obtain a meaningful result. One needs at least about 20,000 events in those intervals. Yes, this is the end of the talk. Thank you very much for your attention. Feel free to ask me any questions. I hope you have a great time at the remaining rest of the Stochastic Tage.